Hello everybody, welcome back to our channel. In this video we're going to be solving this Physics 7B momentum practice problem, Kate and Mike on the mountains. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps this channel. So the problem statement goes as follows. Feel free to pause the video in order to write the problem so that you can follow along. So we have Kate and Mike and they are basically in the mountains. They need to cross a frozen lake in order to reach their next destination. Mike is initially sliding east and Kate is moving 10 meters per second at a 30-degree angle in the northwest direction, and she is carrying a loaded sled. So Mike and Kate have the exact same initial mass and the sled weighs exactly half of that. So at the beginning of the problem, Kate kicks the sled behind her, she breaks the rope, and then the sled basically stops. After Kate separates from the sled, she reaches Mike and grabs onto him. Both of them continue moving together at 60 degrees in the northeast direction. Assume that the lake is frictionless. So there are several things that we have to do here. First of all, calculate Kate's velocity after she separates from the sled. Then calculate Mike's initial speed and their speed after they are moving together. And then C is just a separate scenario. We'll get there eventually. So as you can see, I have written down the relevant information here, at least for part 1 of my notes. So the first thing that we need to realize by just reading the problem is that this problem basically has 2 stages. So we have Kate moving with a sled, and then she's separating from the sled. That will be the first part of this problem. And then the second part of the problem is where Mike gets involved, because Kate basically crashes with Mike and then they are moving together. But when you think about it, Mike doesn't really have anything to do with the first part of the problem. The first part of the problem is just Kate and the sled. So the first question is, calculate Kate's velocity after she separates from the sled. Show your work. So I have all of the relevant information here. Kate and Mike have the exact same mass, so I'm just going to go ahead and call that M for the duration of this problem. And the sled is exactly half of that mass. So in order to just use M on the entire problem, whenever I'm talking about the mass of the sled, I'm just going to write M over 2. That should make things easy. Now, at the beginning of just this part of the problem, so just part 1 right now, Mike is not involved here. Kate is sliding with the sled. So they are basically sliding together. And then the final here is that the sled stops because Kate pushes it. And then she is just moving on the exact same direction. So both of these, initial and final, are happening at the exact same angle. That didn't really change. We didn't change direction. The only thing that changed is that the sled was moving here and now the sled is not moving here. So we need to figure out what is the final velocity for Kate. So let's just go ahead and do that. As you can see, I have a momentum chart over here. This is going to be really useful in order to solve this part of the problem. So let's just go ahead and fill that in. So let's just do initial for Kate, initial for sled. So as you know, momentum is just going to be mass times velocity. So I'm just going to go ahead and do, so another thing that's important here is that something that's going to make this problem easy is that we're not really changing directions here. So I can just use absolute values over here and just keep everything within this line. So instead of worrying about this 35 degrees, I can just work with the magnitudes of the problem, and that is going to work on this part right here. So let's just go ahead and do absolute values. So initial momentum for Kate is just mass of Kate, which is M, times her initial velocity, which is 10. So she is 10 M. And for the sled, the mass of the sled is M half. And the initial velocity of the sled, because they are moving together, that will be the exact same velocity as Kate. So that is also 10. So that is equal to 5M. So if I go here and complete, let's just draw this. So there is some angle. So this is magnitude 10M. Then this is magnitude 5M. And then this plus this has to be equal to total. So this is going to be 15 m momentum. Now, remember that for this part over here, the total change in momentum for the system, this is reserved for external forces. And this problem is saying that we need to assume that the lake is frictionless. So because we don't really have any external forces acting on this problem, we're gonna put a 0 over here. And now remember that the rules of the momentum chart say that all of the rows have to add up. So if there are no external forces, momentum is conserved on the system. So we're just going to go ahead and write a 15 magnitude over here. Now, the next thing that we know is that according to the instructions, after Kate pushes the sled completely stops. If the sled stops, that means that its final velocity is equal to 0. And because, you know, momentum is just mass times velocity, final sled is going to be equal to 0. So we have 0 over here. And now, as you can see, this is very straightforward because we do know that, again, per the rules of a momentum chart, the column has to add up. So something plus 0 has to be equal to 15. That means that Kate has a final momentum of 15 m. And now we could very easily just complete this chart right here, right? Because this plus this has to be equal to 15, so that is just going to be 5 here. And then 5 plus something has to be equal to 0, so that is going to be, oops, that is going to be 5 in this direction, I'm sorry. And then this arrow plus this arrow cancels. So the momentum chart is complete. So now we have the final momentum for Kate, but the instructions are asking us for Kate's final velocity. But that is very straightforward because, you know, the final momentum for Kate is just Kate's mass times times her velocity. So 15 m is equal to mass times velocity. So that means that her velocity, you know, magnitude is equal to 50 meters per second. And that would be it. So that would be final answer for part A. Now, before we move on to part B, I'm just gonna go ahead and separate her final momentum into X and Y components, because all of these arrows, you know, it didn't really matter because all of them have the exact same angle, but they do have an angle. So it is actually very important going into part B that I separate this into X and Y component. It's just gonna be useful. And you'll see why in a second. So her, the magnitude of her momentum is 15 m, and she has this angle over here. So if I separate this into X and Y component, then her X component is just gonna be 15 m cosine negative of 35. And the Y component is just gonna be 15 m sine of 35. So in vector form, let me just grab a calculator over here. That would be 15 cosine of 35. So that is negative 12.28 m. And then 15 sine of 35 is equal to 8.60. Oh, m. Yeah, times the mass. So this is her final momentum in X and Y component, and this is going to be useful going into part B. So this is the end of part A, so let's just go ahead and move to part B. As you can see, I have a separate piece of paper for part B. The only thing that I'm gonna copy right now is Kate's final momentum. So she is a negative 12.28 m and then 8.60 m. Okay, that is the only information that I need. Moving on to the next problem. So in this part of the problem, Kate is already, you know, detached from the sled. She is moving and she's gonna hit Mike. We don't know Mike's initial speed, but we know that he's moving east. And also, once they hit each other, We don't know their final speed, but we do know that they are going 60 degrees north of east. Now, for this particular problem, this part was important because Kate's initial momentum is her final momentum from part 1, right? So she is detached from the sled, she has a new velocity, she has a new momentum, and this is going to be her initial momentum. So I can just go ahead and write that down. But again, this is her initial momentum for this part of the problem. Oh goodness, 8.16. There we go. Now, we don't know anything about Mike except that he is moving completely on the x-axis. Well, actually on the east. So Mike is gonna go east. We don't really know the magnitude, so I can't really put that on the momentum chart. And also, we know that whatever their final speed is, they are going 60 degrees north of east. And this is where the problem kind of gets a little bit tricky, because we know that Mike, let me just put some arrow over here, magnitude, I'm just not going to be able to represent it because I don't know the magnitude, but he is going east. And then whatever this is, they are moving together at a 60-degree angle at the end. So let's just go ahead and try to make up some sort of triangle over here, right? Because we know that this arrow plus this arrow has to add up to a total. And because this is 0 over here, we're still on the lake, we don't have any friction. We know that whatever this magnitude is, this angle right here has to be 60. Because this angle right here, the instructions are telling us that it has to be 60, and because Mike and Kate have the exact same mass, their momentum is just gonna be half and half of that. Again, 60, 60. Again, this is only true because Mike and Kate in this particular problem have the exact same mass. So if there is a total momentum and they are going at the same velocity and have the same mass, they are just gonna add up to twice the final momentum. But we don't know this magnitude, we don't know this magnitude. We just know that this plus this has to add up to a vector with a 60-degree angle over here. So let's just go ahead and try to put up some diagram over here. So let me just start by putting up Kate. So this is Kate. So this over here is Kate. She has an angle of 35 degrees according to the last problem. Her total initial momentum is equal to 15. Yes, so 15. And then this side over here, it's her y coordinate. So this is 8.60. And her x component of her momentum vector is 12.28 just in length. I mean, of course, it's negative because she's going to the west, but I'm just looking at lengths here. So this is Kate. Now, we know that Mike is going to be somewhere in this line over here because Mike is going to the west and Mike is going to add up to Kate in order to give us a final momentum, right? And that is how vector addition works. We do the head to tails method. So Mike's vector is going to start somewhere here and it's going to end up, you know, somewhere in this line. But how can we possibly know the length of Mike's vector? Well, we know that the final momentum, which is the addition of Mike plus Kate, has to be equal. So let me just, this is Kate. So if I add Kate plus Mike, I need to get 60 degrees. So I need to get something that has 60 degrees over here, as you can see. So this is the total momentum. It's going to have an x-axis over here. It's going to have a y coordinate over here. And it's going to be 60 degrees over here, right? And we know that Mike plus Kate has to add up to total. So Mike needs to be this arrow over here. So this is how it's gonna work. If you add Kate plus Mike, you get your total. If you add Kate plus Mike, you get your total. We know that this is 60 degrees, but we don't know what this is. We don't know what, well, actually, we do know what this is, right? Because if you just look at the triangle, Mike is all on the X component. So if you just look at the trig of this problem, we do know that the Y component for the P total has to be equal to 8.60, right? Because it's over here. So we do know that the Y component, needs to be 8.60, and we can actually work with that. So let me just write that information. So the Y component of the total is equal to 8.60, and we can also use this angle, right? Because this 8.60, which is the Y component, is also equal to the total times the sine of this angle. So if we just use this part over here, which is what we know, this information was given, and then this we figure out. But now based on this, we actually can figure out what the total momentum is. So let's just go ahead and do that. So P total is just gonna be 8.60 divided by sine of 60. So let's just go ahead and do that. Oh, I'm also missing the m's all around, but we'll find. These are momentums. Yeah, that's annoying, but whatever. So 8.60 divided by sine of 60 is equal to 9.93. So the total momentum magnitude is 9.93, times the m that we've just been dragging all along. So this magnitude right here is 9.93 m. There we go. So now that we have this, we can actually figure out what this is, right? Because we have 2 out of 3 sides. So that should be easy enough. Let's just go ahead and do that. So let's see. So Px of the total vector, that is just going to be 9.93 m, which is the total magnitude. But now that is going to be times cosine of 60. So if I just multiply that, that is 9.93 cosine of 60 degrees, 4.96 m. So this side right here is 4.96. And there we go. And that basically solves the problem of Mike, right? Because if you just look at the trigonometry of this problem, Mike's vector is just gonna be this chunk right here. So this 12.28 plus this 4.96. So I'm just gonna go ahead and add that. 12.28 plus 4.96. So Mike's vector is going to be 17.28 m. All right, so let's just go ahead and write all of this very useful information. So this is 17.28 and then nothing on the y-axis, so that would be a 0 over here. And then this vector has an x component of 4.96 and a y component, m, and a y component of 8.60 m, both positive because we're going east and north. This vector has the exact same components because I just copied that. And now going back to these vectors again, because Mike and Kate have the exact same mass, we're just gonna go ahead and divide this momentum in half. So let's just do 4.96 divided by 2, 2.48. And 8.60 divided by 2, that is 4.3. There we go. So now we basically just, you know, at this point, I think that we might as well just go ahead and finish out these momentum charts. So let's see. This row has to add up, right? And we know that delta is just final minus initial. So let's just go ahead and figure out what these numbers are. So final minus initial is 2.48 minus 12.28. That is 14.76. And then 4.3 minus 8.60, that is going to be negative 4.3 m. Might be wrong, but I don't think so. And now for this one, final minus initial, so 2.48, 17.28, that is going to be equal to negative 14.75. Oh yeah, and also these two have to add up, so this is just going to be 4.3 and positive. All right, so this is just going to be an arrow like this. This is just going to be some arrow like this, and the momentum chart is complete. Okay, so now just going back to the questions. The question was asking, what is Mike's initial speed? So Mike's initial speed is just Mike's initial momentum is equal to 17.28 m, but momentum is also mass times velocity. So Mike's initial speed is just 17.28 m divided by m. So Mike's initial speed is just 17.28 meters per second. Final answer. And the other question is, what is their speed after they are moving together? Show your work. Okay, well, for this one, they are moving together, so we can use whichever of these three arrows. Obviously, I think let's just go with Kate. I mean, it literally doesn't matter. So P final for Kate is equal to so let's see, we need to use Pythagoras over here, so that is, well, no, yeah, let's just do Kate. So 2.48 squared plus 4.3 squared. Let's just go ahead and do a square root, and that is 4.96. And that is also equal to mass times her final velocity. So the final velocity is just 4.96 divided by m, so that is just going to be 4.96 meters per second. And because Kate and Mike are moving together in this problem, the final velocity for Kate is also going to be the final velocity for Mike. That is just how it works when two things move together. So this is basically the end of part 2 of this one quiz that students had to do. Final answer. So now we just need to go ahead and do part 3. So this is part 3 of our problem. The only thing that matters here is Kate's initial momentum. So her initial momentum is just basically, you know, something like this. And let's just go ahead and read the problem. So after they slide for a while, they decide that they need to get the sled. At the instant that they are exactly north of the sled, Mike pushes Kate and she starts sliding directly towards the sled. In what direction did Mike push Kate? Your answer should be north, south, east, west, northeast, northwest, southeast, or southwest. Explain your answer. Okay, so at this point, our initial condition is that Kate and Mike are exactly north of the sled, but they are moving. And then Mike pushes Kate, and as a result of that push, Kate is now moving south towards the sled. Now, a lot of people in this part of the quiz, especially because they were running out of time, just figured, hey, if you're north and you want to go south, then you need to be pushed south, obviously, in order to get to the sled, right? Well, that is wrong, and you can just see that if you use a momentum chart. So Kate is initially moving in this direction, right? So that would be northeast. And her final momentum is actually south. So if we do a momentum chart, what would be the answer? The answer is Mike didn't push Kate south. Mike actually pushed Kate in this direction, so that if you do your vector addition, you get initial delta, you get a final going down. So there we go. So the final answer is that Mike pushed Kate, what is this, southwest. Again, this was a very easy part 3, but this was a very long quiz, so a lot of people just went ahead and said south just because Kate was exactly north of the sled. But no, because Kate had an initial momentum. So when you have an initial momentum, you need to adjust your delta P in order to get the final that you want. Pushing south would have only worked if she didn't have an initial, because 0 plus south equals south, but she did have an initial, so that is what makes it not work. However, it was an easy part 3, I think. Well, this certainly was a very long problem. I do like the problem, but it was very challenging. However, it was a quiz for Physics 7Bs, like it was an actual quiz, so I thought it would be a good idea to just put it in here. As usual, if you're finding these videos helpful, please leave a like and subscribe. It helps the channel a lot, and I'll see you guys on the next video. Bye!